Hey, Guyan.
Hello. Uh,
Hello.
yeah, maybe let's wait for 5 more minutes and we can start our seminar today.
Sounds great.
Yeah, we will record our seminar and we will upload to our YouTube channel.
Sounds great. Yeah. The last recording didn't come up, right?
I'm not sure. I will check it. Uh,
I had the last recording. I had sent it. It should be on the YouTube channel.
okay. Yeah, good.
Mm, cool. Okay. Shall we start?
Yes.
Yeah, you can start.
Yeah.
Okay. Hello everyone. I'm Ashwin. I'll be talking about your intermediate Python programming tutorial. So I was asked to speak on statistical analysis, but it is a boring topic, to be honest. So I have also included. I'll also be talking about optimizing code so that you get faster calculations. Uh, I must note though that to before you optimize your code, you must be You must actually make sure that your code is actually working first. Unless the code is working, going into optimization is going to break your code no matter what, and it's very difficult to fix afterwards. To start off with, we have for the agenda, we have statistical analysis on data sets, which I'll just skip over briefly. I'll be talking about Python and as to why it is slow, and I'll also talk about how we can make it faster. We'll be talking about multiprocessing and Numba. Numba is a package which we'll get to later, and then GPU computations using Python is also pretty easy using Numba. So we'll talk about all these things. Starting off, data analysis. So in this, let me just restart everything and run the cells one at a time. I believe Alex will share the link to follow along the course as well. The codes have been uploaded to GitHub, and you can access it. And the environment file has also been shared, so you can download it and run the code alongside. So first off, we are importing a few data sets. We are loading. I'm importing a few packages, and I'm loading the iris dataset, which is which we are going to be analyzing in today's talk. So we have 4 features: sepal length, sepal width, petal length, petal width, and we have the type, which is the classifier, which is what we have to classify based on the sepal length and all the other features. Coming to analysis on the dataset, if you take a look, pandas has a few inbuilt functions which we can use. So iris, the data set is stored in a data frame called iris, and it has the iris data. This is a sample of 10 columns from the iris data frame. If you take a look here, it gives us the column names. So iris column gives us an array of column names. The shape gives us the shape of the data set, which is 150 rows and 6 columns. And the size is basically 150 into 6, which is the total number of cells present in the data set. And number of samples available for each type is basically the number of, it shows us that there are 50 zeros, 50 ones, and 52s in the entire types column. So we know that there are 50 type 1 flowers, type 2, 50 type 0 flowers, and 50 type 2 flowers. Then we have iris.describe. This is a very important function for 2 reasons. One is it has all the data, all the summaries of all the columns in it. And 2, it is a data frame. So it can be accessed is exactly similar to how you would access the original data frame. So for the serial number, it shows the total number of elements in the column. It shows the mean of the column, standard deviation, so on. Quartiles. So 50 percentile would be your median, so on. Now coming to covariance. Please let me know if you guys have an issue following along the conventions. I'm just talking about how we can calculate this using Python, and I'm not going into the mathematics of each statistical function. Do any of you have issues with the functions itself, the mathematical background behind the functions? Please speak up.
No issues for me.
Cool. If anyone do have any questions, do let me know and I'll explain it further. So the covariance of a data set can be found using just a simple function inbuilt into pandas called cov. Running this, as you can see, you find the covariance between the two between each column, and along the diagonal of this matrix, you are going to find the variance of each column. Coming to correlation, it is the mathematical equation is so and so, but the function to calculate correlation is also inbuilt into pandas and is dot cor, and this gives you the the correlation between all the features. Now, this is difficult to comprehend. So usually we plot heat maps to view the correlation data. This can be done using SNS, which is basically imported here. But I will not go into the details as to how Seaborn works. It is basically a wrapper around Matplotlib itself, and it makes using Matplotlib easier using SNS. You don't have to import Matplotlib to use this though. But for just as a basic heat map is a built-in function in Seaborn, and you just provide the data and it automatically plots the heat map for it. There are a few more extra features. As you can see here, since the correlation, the negative correlation between the values is just between 0.4 and 1, it is minus 0.4 and 1, it doesn't extend through. To make it more visually appealing, we can just set Vmin and Vmax as -1 and 1, because the correlation value lies between -1 and 1 in general, and it plots it over that range. And so the colors are, you can see the colors more distinctly. The anode is an argument provided into the heat map just to make sure that the values are plotted inside the boxes as well. And heatmap.setTitle is pretty self-explanatory. You can change the color of each of the boxes. So here I'm setting the CMap to be BRBG, which changes the color to look something like this. Now, as you can see in a correlation map, the values along the diagonal is always going to be 1, because the correlation of a single column is going to be 1. But the values above the diagonal and below the diagonal are all equal. And if we remove the diagonal and anything above or anything below it, the information obtained from the graph is pretty much the same. So we can do this using a mask. So as you can see, NumPy has a function called try up and try down, which results in a square matrix with try u, as in try upper gives ones on the top, and it includes the diagonal as well. And try L gives you a diagonal, which gives you a diagonal matrix, which gives you a square matrix with the diagonal and the lower part of the matrix being ones. So if we run this and use it as a mask, as we use it here, it shows only the lower part since the upper part has been masked. Similarly here, since we are using try L, it results in the lower part being masked and the upper part showing up. Any questions about correlation and covariance? Okay. PCA is principal component analysis. This is a very useful feature useful technique used by data scientists to reduce the number of features in a data set. There is data loss when you use this function. So please note this before you use it, but it helps in speeding up calculations because of the low dimension of the data set. So this is a pretty simple way of implementing PCA over the IRIS dataset. So since we have 4 features, I want to use just 2 features, but I want to get the maximum variance from the entire dataset. So that is when you would use PCA. You can get up to 4 components because we have 4 features, but using 2 features would result in something like this. As you can see, the different types of flowers have split up. Yes, there is an overlap between the between 1 and 2, but suppose we add in a third principal component, it would get better, and there would be no need for the 4th principal component. It helps us reduce the number of dimensions required to model our data. That's about the statistical part of the talk. If you guys have any questions, please let me know. I know I did move over that pretty quickly, and the code is available for you guys if you want to look into it mathematically as well. Any questions about the statistics, or can we move on to actual optimization of Python code in general?
Hi, Ashwin. I do have a question.
Yeah, sure.
This is Mrinalini. Yeah.
Yeah.
So I particularly didn't understand why would someone want to reduce the features, because that would obviously result in a loss of data, right? And if I mean, as per my understand of statistics, the more spread out the data is, the more less occurrence of the error. So why
Yes.
would I want to, and in an application perspective, why would I want to
Now,
remove?
suppose you have two features which are very highly correlated. All right. So
Okay.
the second feature is not going to add anything statistically to the first feature.
Okay.
So it is just going to increase compute time, but it is statistically not required for the model. So now suppose you have partial correlation between two features, but you can't eliminate either. But you want to include all the variance from one feature into, you want to group it all together. So that is when you would use PCA. So principal component one would have the maximum variance, say around, suppose each of these features have 25, let me just go over to the data set. Yeah. So assume that each of these has 25% variance. It's not true, but just assuming that's the case, when you do principal component analysis, the principal component of one would have maximum variance. So say it would have 50% variance, principal component two would have 75% variance, third would have, say, lesser than that and lesser than that. You get it, right? So just using two of these, you got a total covariance, total variance of, say, around 75%. But if you use all four features, yes, you get a lot more. But you, instead of using just two features from the data set originally, you would have got just 50% that way, but here you got 75%. It is to
Yeah,
optimize the model.
I understand. Yeah.
You get it?
Yeah, I got it. Thank you so much.
Sure. Any other questions? Anyone? Cool. Let's move on then. Python, uh, in general, is a very slow language. In fact, if you compare it to C or C++, Java, in fact, it is depending on the use case, it is sometimes even 1,000 times slower. So why do we use Python? Well, because of its simplicity. It is easy to use. It looks very similar to your code, your pseudo code, and it can be read by pretty much anyone. But there are times when you want to speed up calculations. So suppose you're working on extremely large data sets and you're, say, running some simulation, or you're training a reinforcement learning model or something. And you would assume that since C or Java is faster, you would prefer to use that because, training times reduce drastically. True, but it is really difficult to build models in other languages because it is not user friendly. There are ways in which we can speed up the Python programming, your Python program to, if not match, you will probably not get faster speeds than that, but if probably slightly slower, or probably match speeds of C or C++. These can be done using multiple ways. There is something known, how many of you know what is a typed language? What is typing in programming? Okay, so Python, typing is defining the data type. So if you have a variable X, in Python, X can hold either hold either a string or an integer at different times in the same program. But most programs don't allow this. So you have to define the data type of a variable at the beginning. You have to declare the variable. So Python is called as a dynamically typed language, so it can change data types easily and it doesn't have to be defined. Other languages are statically typed languages. So you define X as an integer and it remains an integer throughout the entire program. Of course, you can make variables dynamically typed in C as well, but it involves destroying variables and then recreating them, which it is not as simple as doing it in Python. So to make a Python program faster, all we need to do is make it statically typed, and that's pretty much it. But the problem is statically typed languages need to be compiled and not interpreted, and Python is an interpreted language. uh, C++ build machine code and then you run it off directly. You can run it with just a kernel, and you can run a compiled C program. However, but with Python, you do need to have the interpreter at all times. So to do this, to do the compilation, there are multiple interpreters available which compile it into C and then convert your Python code into C and C code into your object code. So one of the most popular ones is Python. I do want to note, I want you guys to note down that Python is not C Python. C Python is the regular Python interpreter which you guys use every day. Python is a specialized interpreter which first compiles your code into into C code, and then your C compiler on your system. If that is on Windows, it is probably Visual C. If you're using Linux, it's probably GCC, and on Mac OS, it's CLang. Uh, that compiler is going to compile the C code into an object code. It is pretty popular for the reason that it supports a wide range of Python functions. It doesn't break easily, but it has an extremely steep learning curve because you need to know C before you use Python, at least to some extent, and you also need to make sure that the program is functional and it doesn't have any non-functional parts in the entire script, which is usually not feasible for data scientists. Then comes PyPy. Uh, PyPy is again extremely popular, but it has a steep learning curve. Uh, I don't use it. I do not know much about it, to be honest. But what I do use is Numba. Numba is a very simple uh, it is a very simple compiler, but it is an interpreter, but it is installed very similar to a package. It is called in the function very similar to how you would call perhaps pandas. It is very simple to use. It requires very minimal changes to your code. So Numba is preferred for data scientists. Now, to show an example here, this is a simple program which just adds two vectors and returns a vector with all the sums. I'm going to create two vectors here which just comprise of ones, both comprise of just ones, and it contains 100 million elements in the entire array. The reason for such a large number is to showcase the time. If we choose lower numbers, it's really difficult to see an improvement or so. So with 100 million elements, if I run this script, it is going to take approximately 35 seconds, right? Let's just wait for this to run. However, as we showed in the beginning, adding, as I talked about this in the beginning, typing the variables out in the beginning help increase the speed. So if we just instead of c.append, which means that the variable c is dynamic. If we just make this a static array, we have without appending anything, we get slightly improved speeds. This is not explicit uh, typing, so this is not completely static. It is pseudo static assignment in a way. So this took 39 seconds. This would probably take around 35 seconds. It is not going to be a large improvement. However, since Python runs only on one core, we can unlock the Python's interpreter to run on multiple cores. This can be done by using a function called multiprocessing. However, please do not use this method. This method is terrible. It can crash your computer and it can even corrupt the data on your hard disk. I will run this because I have tested this out and I have tested it on a virtual machine already. So this script is safe, but please not run this script on your own hardware. The problems with multiprocessing is that it doesn't work with IPython kernel, which is what a Jupyter Notebook is based on. So I have to run a .py file which has this script in it. Let me just run this, and it reduces it pretty quickly. I'll split it into 6 processes because I have 6 cores, and it should probably take around 8 to 10 seconds to run. It is the same calculation as what we did here. As you can see here, there was an improvement from 39 seconds to 37 seconds. Not a huge improvement, but here it took just 11 seconds for the same amount of calculations. Now, when it comes to Number offers the same functionality as this with a lot more. Number, what it does is it first compiles the script into a C program in a way, but it doesn't give you a C file. Instead, it just caches it inside the memory. So the first time you run the script, it is going to take the same time as running it regularly. However, if we run it the second time, since the code has already been compiled, it's going to run much faster. Here, I have just compiled it once with a small array just to make sure that the code has been compiled, and then we can run it for the large number of elements, and you can see the improvement. The basic syntax is just from Number you import njit. JIT was the original function, but you need to make sure that if you use JIT like this, you need to make sure that you use no Python equal to true. This makes sure that the Python interpreter is not interfering inside the program, and so it doesn't reduce speed. Now, the developers from Number realized that no Python is equal to true is probably going to be used by most people, and they created a new function called njit, which basically JIT with no Python in it. Running this script for the same number of calculations, it should take a pretty reasonable amount of time. So we got this in less than 3.8 seconds because the code was already pre-compiled. This is since it's compiled, it is static. The data types are static, and so that is what gives you a very good time for which gives you a very good score here. The thing is, you need to make sure that the data types here. So suppose here you have defined C as an array, but if you then assign C as some integer, it is going to give you an error. You cannot change data types, which we generally take for granted when it comes to Python programming. We do it a lot. We convert NumPy arrays into lists, and we compile lists into data frames, for example. Or we should not be doing any of that inside the function which is set as ngest. How many of you know about this notation, at and then adding a function at the beginning? So this is known as a decorator. So what this is equivalent to is, instead of doing this, you could just do something like, say I want to name the function func. Func is equal to ngit of vector at GPU, and then I could just call func and then give the arguments into it, just as we are doing here. Uh, a decorator basically takes the function itself as an argument and spits out the same function. So NJIT has been built in such a way that it can be used as a decorator.
So does it mean that we don't have to define the function? I mean, you avoid like
You do
when
not
you
have to
usually
redefine the function. Yes.
yeah, okay. So because
It,
normally I have not done this, and normally we do like definition calling and then like usage of the function. So
oh, no, that is in C or in Java. You predefine the function in Java. Python doesn't have
yes,
a predefinition of functions. Python, again, as I said, is a dynamically typed language. So you don't need to define anything in the beginning. All right. So this took just 3.89 seconds. Now, if we add multi-processing into this, which is basically using the multiple cores which we have, there is a safer way to do it using thread pool executor, but it does not automatically remove the GIL lock, which is basically, which I think I explained it somewhere around here. Yeah. Global interpreter lock is what prevents Python from using the multiple cores on the system. So if you want to use multiple cores, you need to make sure that GIL is unlocked. It is really difficult to do this without with just a pure Python, and NJIT makes this very easy for us. As you just specify no GIL inside and you just specify it as true, and it makes sure that the function runs on all your cores, all the processors you have on your system. So if you run this, we should get a better time than we have here. This took it just took 0.2 seconds. And as you can see, the code hasn't been changed at all, other than pretty much just this line and you're importing a package. But other than that, there has been no change as such. Of course, for multi-processing, you need to make sure that you add this, you need to split it into multiple threads. But other than that, it is pretty simple Python scripts. Now, to showcase this as how it would have an effect on simulations, I'm using a Python simulation for rigid bodies on a spring. Yes, it is not used by most of us in data analytics engineering, but I didn't really want to mess around with the reinforcement learning model for this, and I found the script online. I found the simulation online, so which is what we'll be using here. So what you need to know is that the simulation is pretty simple. You start at a point X, and you want to make sure, you want to find out as to where the spring, where the object finally lies. And since we have different kinds of friction, depending on where the spring starts, it is going to find equilibrium at a different point. So we want to run this over different values. So over different locations per se. All right. So running the simulation over from 0.1 would give you something like this. The amount of time it took to run the simulation is around 280 seconds, and the time it takes to run the simulation is not dependent on the value here, because it's just the initial value. So assuming that it takes 280 milliseconds for one simulation, and if we want to run between 0 to 100 on 0.1 increments, it is going to take 2,800 seconds to run all the simulations. And that is basically 46 minutes. Now, if we want to optimize this just by adding NJIT on top, the time is going to be reduced significantly. Here, I'm just verifying that the results are the same as here, so we need to make sure that the program is not broken. And then timing this, we see that it is just a millisecond. The last time I ran this script, it took 2 milliseconds. So that is why I have this. So assuming it takes now just adding NJIT at the top reduce the time by a lot. It's just 10 seconds for all the simulations together. Now, suppose we want to, if we think that 10 seconds is a very large number and we want to add multiprocessing into it, how long would it take? Well, it is taking a lot longer than what we thought it would. It took 19.3 seconds. Assuming this was 2 seconds, it basically took the same time as we predicted here. All right. So the reason is thread pool executor does not automatically remove GIL, and we need to make sure that GIL is unlocked. So using NGIT again, we can just specify that it is unlocked, and if we run this script, we see that the time is much lesser. It just took 2.5 seconds instead of the expected 10 to 20 seconds, which we calculated on top. So these methods are great, but thread pool executor is not as stable as, say, inbuilt NJIT. So NJIT in itself has an ability to split processes, and I would suggest that you don't use thread pool executor, but rather use NJIT itself. It is most of the time it is actually more efficient than the thread pool executor itself. So taking a look here, if we run it without with the inbuilt multiprocessing functions of NJIT, we basically use something called prange, which is basically range, but it splits everything into multiple processes. It is as simple as that. So running this, we see that it takes it took 2.05 seconds. Here it was 2.5 seconds. These values seem small. The gains here seem very small, but in the long run, if we run reinforcement learning models, take hours and hours to train. If we over that large period of time, this is a really large saving. When it comes to GPU computations, Number has built-in GPU computations as well. So all you need to do is specify target is equal to CUDA. I need to mention here that if you have an AMD GPU, this won't work. You need to make sure that you have an NVIDIA CPU, NVIDIA GPU, and you need to make sure that you have CUDA installed as well. There are open source versions for AMD. I think it is called OpenCL, but it is not as advanced as CUDA. But then again, I'm not a fan of CUDA either. It is closed source. I'm a real fan of open source programming. But that is what we have, and all the packages support CUDA really well. I just want to show you how this computation works on CUDA. This is a function which returns 1 if the value is even and returns 0 if the value is odd. If we and I'm running it over again 100 million values to just to check, just to make sure that the function is working, we are just sending it values 1 and 2, and just to make sure that the function is right. So we see that 1 is even no, and 2 is even yes. The function used here is called vectorize. This is again built into Number. So you import vectorize from Number. How it is used is it basically makes sure that the value which you send in here is converted into a vector. So you can send in integers, or you can send in floating point values. You can send in arrays of integers or arrays of floating points, and it makes sure that it is all converted into a vector, which is really easy for us to manage, as the final return value will also be an array if the input is an array. It functions really well, and it is completely optimized within itself. It optimizes the function automatically. So here I'm just testing it. Here we did it over a single integer. Here I'm just generating, let me just print this out. So I'm just generating values between 1 to 20 and then just checking it. And as you can see, it returns an array, though it is the same function. Now, the test list which we have here is again 100 million values. If we run this over regularly over this, it is going to give you, it ran the entire calculation in just 202 milliseconds, which is really fast, right? I unfortunately have not written a benchmark to compare it over normal Python syscalls. Anyway, we can try the same thing over the GPU. All you need to do is make sure that you add target is equal to CUDA. GPU calculations requires you to specify the input type and the output type, but it need not be an array. You just need to specify what kind of value is going to be calculated and what kind of value is given as input. So if the array contains integers, all you need to specify is integers. Even this still accepts single integer values. So running this, we are again creating a list of 1,000 elements, 100 million elements, and we are declaring the function and checking it. It returns an array, 0 and 1. But now if we, let me just print this out again. This is again testing it over an array and it still returns an array. But if we time this, it took 175 milliseconds, which is faster than the function call with just CPUs. It is not necessary that the GPU is going to give you a faster calculation. In fact, here it might be just noise, and in general, it would give you a pretty equal time. But over larger calculations, GPU would be more efficient than the CPU because it has more CUDA cores in it. How many of you know about CUDA? Do anyone of you have any of you used CUDNN before?
No, I only have a vague idea about CUDA and why is it used for.
Okay, so GPUs are graphical processing units. So why do we use it for calculations on for these kind of calculations? So GPUs have something called as CUDA cores. At least NVIDIA GPUs has something called CUDA cores. Other AMD GPUs have, I don't really know what they call their the cores, but they do have cores, and these cores are really good at approximating values. Uh, Approximate calculations can be done extremely quickly on these processes because graphics is basically approximation of colored values. All right, we do not. The better the GPU, better averages you get. Yes, but we do, in most cases we do not require extremely accurate calculations. What the GPU does is, even if you provide an integer input and an integer output, it converts it into a float, then does the calculations, because GPUs can only run floating point operations. That is perhaps a reason why this is giving you at 175. If we probably input a float 8 and a float 32, it would probably give you something faster. Anyway, coming back, so that is how a GPU calculates things. Since it has multiple cores, it can do a lot of parallel processes at the same time, and which is why we get extremely fast calculations. All right. Moving on. Here we have here this is, yeah, this is basically the same calculation which we did at the beginning, which was adding the 100 million elements. If we do it on the GPU, we can see the gains, the speed gains. It just takes 0.6 seconds. Here, the best we got was, I think, 3.2 seconds or so. No, we got 2.05 seconds. This was the best over multiple cores and all the optimizations added in. With the GPU, it just took 0.6 seconds. So as a data analyst, how would you use this? And is there an actual advantage to using this? The advantage of using this is only if you have large data sets. Otherwise, it's not worth the time to actually make sure that the code works with multiprocessing in it. But given that you have a large data set, how much of a performance gain would you get? So this is a very basic function to calculate the standard deviation. We calculate the mean, then we calculate the variance, and then the square root of the variance gives you the standard deviation. This is the simple this is without any optimizations, and this is adding in just NGIT. I'm not even adding any multiprocessing. There's no multiprocessing being done here. It is using just the only advantage which you're getting here is from dynamically typing converted into statically typed. So running this over, I'm just going to compile the code here for first, and I'm just going to generate an array with again 100 million elements with a mean of 0 and a standard deviation of 1, so that we can make sure that the values we get out as output are correct, right? And it has compiled, and we have an array of 100 million elements. So running this script as you would generally do, which is without any optimizations, is going to take approximately a minute. It is a really long time, right? Let's just wait for that to complete, and I can. So the reason why I can't run another cell in parallel is because of the GIL lock. So we have to wait for this script to finish. But while it is running, any questions? Anyone?
I had a question about running this all on Google Colab. Is it similar to this in any way, or is that a totally different process?
No, Google Colab does support number, and GPUs are available on Google Colab.
Yeah.
I have not tried running this on Google Colab, unfortunately, but let me just create a new notebook, and let me just try to have you used the GPU on Google Colab before? It is pretty simple. There has to be there's an
Yeah, so I have I'm actually running a reinforcement learning model right now on it, but the thing that I don't know is if it's actually using the GPU or not. Like I can't tell if it's actually
have you specified in your code that it has to use the GPU?
I'm not sure. I think I tried once, but it didn't make a big difference.
Which package are you using to use the GPU? Are you using PyTorch? Are you using TensorFlow for the model?
TensorFlow. TensorFlow.
So TensorFlow has this. There is a function called check GPU. I think is in TensorFlow. I know it in PyTorch, but TensorFlow check GPU. So you just run this script, run this command in one of the cells. If it gives you a true, if it returns true, it means that the GPU is being used. It is just a one-line command. PyTorch has PyTorch is much more suited for academia. The reason is it is more user intuitive like Python. TensorFlow is meant for industrial use. Yes, TensorFlow is faster than PyTorch, but again, it comes between to balance the two. Do you want speed, or do you want user friendly? Do you want it to be user friendly?
Yeah, I actually had a couple of problems with TensorFlow, but we don't have to go into that now.
So TensorFlow requires you to explicitly install CUDA, which is pre-installed on the Google Colab. But if you want to run it on the system, it is a real hassle to get it started.
Yeah.
PyTorch comes with its own CUDA library. It is so it is much larger, but it works out of the box.
Okay. I see.
Do give PyTorch a look. You would appreciate it.
Okay, I'll look into it. Yeah, thank you.
Sure. So here it took 1 minute and 15 seconds to run the entire calculation for the 100 million elements, and we got a standard deviation of 0.999, which is pretty much 1. Now, if NumPy has a built-in function to calculate the standard deviation, and that should take 625 milliseconds. All right. But if we use our optimized function, do you expect it to be faster than this, or do you expect it to be slower than this, which is the inbuilt NumPy function? Anyone? Okay, let me just run this. And it took less than half the time that NumPy itself, NumPy's inbuilt function takes. So using this in such cases is definitely useful. I guess that is the end of my talk. If you guys have any questions related to using a GPU, even if I have not spoken about it in the course, please let me know and I can answer the questions now. We do have time. Questions about anything on the talk, or even anything about Python, you guys are free to ask me.
I have a question on TensorFlow, but I don't know if you want to go into that.
Sure, go ahead.
So I'm running a, as I said before, I was running a reinforcement learning algorithm.
Mm-hmm.
And one thing that I noticed is that, so I'm doing a double DQN algorithm. So it's doing a train for every loop in the episode.
Mm-hmm.
And one thing that I noticed is that the performance slows down a lot as the number of episodes increase. Like it starts out, going fairly quickly, and then once it gets to the end, it's doing like.
Yes, that is pretty common, and that is not because of Python. That is because of something called a CPU throttling.
Okay.
So as the CPU heats up, it needs to reduce the number of clock cycles so that it can cool down. So that is the major reason for it. There are ways to, if you run it on Google Colab, it is going to slow down a lot because they use the at least the free version of Google Colab doesn't have, it is not overclocked in any way.
Okay.
But if you do run it on your system, there are a few optimizations which you can do. How about you drop me a message on Teams and I can show you what I have. I haven't done it explicitly for TensorFlow. I have done it for PyTorch, or rather I'm doing it for PyTorch at the moment. Even I'm working on a reinforcement learning model right now. Yeah. So I can show you the optimizations which we can do.
Okay. Yeah, great. That would be awesome. Thank you.
Cool. Anything else? Mrinali, any questions?
No, I'm good.
All right then. If that is it, Alex, can we have? Is that it? Do we need to do anything else?
No, that's it. I'll send the recording, so it'll be posted on the YouTube channel.
That sounds great.
Yeah, if no one has questions, we can end it here. And thank you so much.
Yeah, thank you.
Thank you.